right, so you can see that we're treating this allylic system with molecular bromine and high energy light. And so whenever that bromine and light, or that bromine is irradiated with light, it's going to undergo a homolytic cleavage, produce two bromine radicals. Right? The strength of that bromine-bromine bond, just like whenever other radicals form, it's based upon the bond strength, and this is a pretty weak bond at 193 kilojoules per mole. Right? Those bromine atoms are big; they're going to be far apart from each other in bonding, and so it's relatively weak bond, and therefore can be homolytically broken just with high energy light. Right? In terms of a radical chain reaction, this is a propagation, or not a propagation, initiation step.
Sorry, I have a quick question.
Sure.
Do all diatomics undergo homolytic cleavages?
They can't, not fluorine. Fluorine's, as we talked about, it's kind of its own special thing. But chlorine does, bromine does, iodine does, yeah.
Gotcha.
Other questions? Okay, so once we have our bromine radical, be able to abstract a hydrogen, right? So bromine's going to grab a hydrogen, and that's going to leave behind a carbon radical. And hydrogen bromide. Right? And if we look at where that radical is being formed, why does that radical form specifically in that position? Sarah?
In conjugation with the pi bonds with the liquid.
Good. So it's in conjugation with the pi bond, right? And it's also far away from the really sterically bulky terbutyl group, right? So we have two allylic positions, or two positions where if we form a radical, that radical will be in conjugation with the pi bond. But one of them is kinetically much more available, right? That's going to form a lot faster than a radical at the other position, just because that terbutyl group is blocking access to that other carbon. Right, once we form that radical, so this is a propagation step. Right, we're starting with one radical, we're forming a different radical. Right, that carbon radical, once it forms, is going to react with bromine, molecular bromine, and continue the chain. Right, so make a bond of bromine, that gives us our product. And a new bromine radical, which then can continue the chain reaction, the radical chain reaction. Right? Whenever you're showing product formation in these radical reactions, you typically want to show that product form through propagation, right? Because we're trying to keep the termination events in these reactions at a minimum, because that ends that radical chain reaction. Questions?
So how exactly are we like avoiding this going through like regular halogenation?
Good. So anticipate side reaction. So what else can happen?
Halogenation.
Yeah. So imagine if we do this, right? We learned a reaction where we're reacting with the alkene, and that's going to give us dihalogen. Okay, so that's a really good question. How do we avoid that?
You need to like break down as much bromine like first with like the light, like make as much of it as go through the.
Yeah, so good thought, but we can't, yeah, that doesn't really work like that, yeah. So Joey suggested we break down the molecular bromine so we don't have that molecular bromine in the reaction. That's a viable strategy, but just not the way that you're suggesting, not by breaking down molecular bromine.
Make it colder?
So there might be a kinetic effect, right? So maybe the radical halogenation is a kinetically faster reaction, and this is a slower reaction. So by making it colder, we can maybe reduce the side reaction. I don't know if that's true until we actually run the reaction. Right? What's one thing, if you look at the reagents conditions on these reactions, what's one thing that's not clearly spelled out in the conditions of the reaction?
The solvent?
Solvent, yeah, right. So the solvent's going to play a role. So if we were to do bromination, right, bromination of an alkene or alkene addition, what types of intermediates are you forming? Are they charged intermediates? Are they neutral intermediates? Yeah.
Doesn't it create the tetrabutyl shape? Or not tetrabutyl, the, what is it? The bromium? Brominium?
Good, bromonium ion.
So it's charged.
Yeah, so one of the intermediates that we're forming here right, is this intermediate here. So this is going to be a polar intermediate. Right, and so if we're forming that intermediate, even though we want it to react, we still need to be able to form that intermediate. Right, so what type of solvent would we use for this reaction? We're making polar intermediates.
A non-polar vertical.
Probably want like a somewhat polar solvent, right? So we can actually form these intermediates.
Oh, I thought it would be that it would react with them.
Yeah, so we want something like, I mean, not like super polar, we don't want something protic, usually like ethanol, right? We don't want something that can react with that bromonium alternatively to the bromide that's in there, right? But usually something like THF, dichloromethane, diethyl ether, right? So these somewhat polar, lightly polar solvents are usually really good for the bromination reaction, right? For the radical halogenation, the intermediates that we're forming, are they charged? Are they polar? Are they non-polar? Matt?
Oh, they're not charged. I don't know if you count half from the electron low pair, or not pair, just low electron. But
Yeah, so they're not charged, they're not going to be polar, right? And so when we do this reaction, we're typically using non-polar solvents. The one that you'll see often in textbooks and literature, carbon tetrachloride.
isn't it pesticide?
Put a box around this and put some exclamation points next to it. Because this is a solvent that's been banned in a lot of states. Really, really bad, chronic carcinogen. Used to use it like to degrease engine parts for on military bases. But like, you know, I did my grad work in California. You can't buy carbon tetrachloride in California. We couldn't even use it in our lab, right? Just because the state, the entire state says no. So really bad. Nonetheless, great solvent, and is a very good non-polar solvent for these types of reactions. Yeah, another one that could be possible to use in this case is going to be equally as great. Benzene. Right, so not too many good options for solvents for this reaction. Right, but one thing that we could do is use the solvent to our advantage, right? So if we want a polar reaction to go and we want to favor the alkene addition, we'll use a more polar solvent. If we're trying to favor the allylic halogenation or benzylic halogenations, we'll use a non-polar solvent, right? The other option is to just use a different reagent in different conditions altogether. So if we use a peroxide radical initiator, all right, and then rather than using bromine as our molecular bromine as our bromine source, we use a molecule called N-Bromosuccinimide. Commonly known as NBS, right? We can get this reaction to go, right? And note about NBS, so if we look at the bromine-bromine bond strength up top, you can see it's 193, right? The nitrogen-bromine bond strength here is a little stronger, 243 kilojoules per mole. Right, so stronger than the bromine-bromine bond, but still relatively weak in the world of covalent bonds. Okay. Take 5 minutes, see if you can figure out the mechanism for this reaction. Right? We looked at the homolytic cleavage of benzoyl peroxide on the first day we talked about peroxide, so I think, or radicals, so I think on Friday. Right? So if you're unsure what happens with this, take a look at the notes from Friday. Right? That's going to be the molecule that initiates this reaction. How many people have mechanisms brought up?
Almost
Do we have one yet? Almost? Good.
Do you drink coffee about over?
Do I drink coffee?
Yeah.
Yeah, probably too much.
Oh, that's that's fair. How do you like your coffee?
Just a little bit.
A little bit of half, no sugar?
No sugar.
I get that. Yeah. Yeah. No, I respect you.
What?
I'm like the type of person I would just drink black.
No, not really.
You are the type of person who'd be like, you know, it's a learned taste.
It's what?
It's a learned taste.
It's an
That's what
acquired
my sister
taste.
says, yeah.
Learned.
It's my bad. Use the right lingo. Literally everyone. I kind of expected like sugar. I'm surprised with it.
Alright, let's take a look at this mechanism. Okay, so benzoyl oil peroxide is the radical initiator, right? So that's where the radical is going to start the formation, or that's where we're going to form the radical from. Alright, so benzoyl oil peroxide, relatively unstable peroxide. This oxygen-oxygen bond is really weak, right? So you don't need much heat. I mean, this degrades pretty rapidly at room temperature even. When you buy it, you have to store it in the fridge. Right, so just a little bit of heat is going to cause this to break apart. Oxygen-oxygen bond to form two peroxide radical, or two oxygen radicals. Right, so this is an initiation step. Right, once we have that oxygen radical, that can abstract the hydrogen from our alkene, our allylic system. Right, so that's going to result in the formation of a carboxylic acid and then a carbon radical. Right, and then another propagation step, we're going to take that carbon radical. Right, and then we can react that with the NBS. And that will result in the formation of our product. And then a new nitrogen radical that can continue the radical chain reaction process. Yep.
So then, in the very last part, like the, what is it called? The NBS, so that will then abstract the hydrogen from the
Yep.
extra.
That'll
instead
come
of
up
the-
here, abstract the hydrogen, right, will form the succinimide, that's what it's called, with the hydrogen on the nitrogen, right, and then we just continue around and around.
Gotcha, thank you.
So you showed us that the pH, horrible names, the carboxylic group off the pH.
Here?
Yes.
Benzoyl
that would
peroxide,
degrade
yeah.
into CO2 and a benzene and an extra radical. Wouldn't that be more comfortable in joining with the thing we're reacting with, the terpene ring? Because they'll form like a conjugate system.
Would, I'm sorry, say it again?
So once it becomes a radical, doesn't it degrade into a?
Yeah, it can, so it can form a benzene radical and carbon dioxide, yeah.
Would that benzene radical react with nothing?
Oh, yeah, so we can get some termination reactions where the benzene radical can react with this radical. But the idea is that we're keeping, I mean, you know, when we put this in, This is just the initiator, right? So the idea is we're not putting in one full equivalent of this.
Oh.
Putting in a catalytic quantity, a substoichiometric quantity. And hopefully the concentration of this or the phenyl radical at any one time is going to be pretty low. And then there's going to be, in the reaction, there's going to be more of the allylic, protonated allylic system and less of the free radical. So, yeah, less likely to meet up. Other questions, Julie?
I'm not sure if this is like important, but what would the final termination step be for something?
Yeah, so I mean, we could think of several different termination steps. The idea is that most of for these radical chain reactions, the termination, we're trying to avoid the termination usually, right? So it's not something that we're creating a lot of product with. So any radical that we're forming in here, any two radicals that we're forming in here can undergo a termination reaction, right? So we can take this and react it with that. We can take two of these, react them with each other. We can, take a succinimide radical and react it with any of those other ones.
So it might not even be super predictable all the time.
I would say it's predictable, but because we're trying to avoid it, it's not going to be a big portion of our product. Yeah, major. Make sense?
Yeah.
Other questions? Okay, so radical halogenation or allylic and benzylic halogenation can happen either way. If we're using bromine and light, we just have to keep in mind that there's going to be side reaction that can occur, and we have to design the reaction and the conditions in such a way to avoid that side reaction. All right, so let's talk about radical dehalogenation. So we can take halogenated alkanes, treat them with AIBN and tributyltin hydride. Tributyltin hydride is a reagent that we're going to see a couple of times in this chapter. Really useful reagent for radical chemistry. And we can get a substitution of that bromine with a hydrogen. Right? In this case, the AIBN is going to be a radical initiator. Right? And again, on Friday, we looked at how that molecule breaks down to form two different radicals. Right? And then the tributyltin hydride, hopefully you can take a look at this and see, oh, I have a hydrogen, so that hydrogen must be coming from the tributyltin hydride. Right? So see if you can figure out a mechanism for this, just really quickly. Okay, and then we'll go over it. So the thermolysis of AIBN forms 2 carbon radicals and then a nitrogen, molecular nitrogen, into.
Yes. Oh my gosh, Carl. I've never seen you jump.
That's all right. When you're working through this mechanism, I'll give you another minute or two. Just keep in mind that the AIBN is just the radical initiator, so we're only putting like 5% into that reaction just to get the radical chain reaction to go. We're using 1.2 equivalents of tributyltin hydride. Right, so the hydrogen that we're replacing the bromine with is coming from the tributyltin hydride. All right, let's go over this. So on the right here on the board, I listed the bond dissociation energies for the relevant bonds that we're making or we're breaking in this reaction. Right, so you can see in our starting material, or reactants, we're starting with a carbon-bromine bond. Yeah.
Does the tin and the bromine have like a relationship? Or?
Oh yeah, they love each other. That's fine. I mean, look at this number, 552. What's that?
That's the Orgos relationship.
Exactly.
Yeah.
Right, so we're starting with the carbon-bromine bond, right, and a tin-hydrogen bond. If you look at the list here, right, the carbon-bromine and the tin-hydrogen bonds are the 2 weakest bonds. In the product, we're replacing that carbon-bromine with a carbon-hydrogen bond, right, and the tin-hydrogen bond with a tin-bromine bond. Right, and those are going to be the 2 strongest bonds. So there's a real thermodynamic drive for this reaction to go, right, if we're making the tributyltin bromide, right? That's really the driving force for this reaction, right? Why the dehalogenation works so well. Why would the tin-bromine bond be so much stronger than the tin-hydrogen bond? Why are those 2 atoms such a great match for each other? Yeah.
Just a guess. Well, tin is a metal, so it has delocalized electrons anyway, and bromine's super electronegative, so it's pulling against that, so the bond would be stronger than it would be the hydrogen.
Tin is a metal, so you have some right things in there, but also some wrong things.
Right.
That's where is tin on the periodic table?
Is it in the T block?
No.
It's
Is it
not.
on the atoms?
Is it rare for bromine? Let's guess.
Frank, you said-
They have more electron overlap,
Good. Why would that be?
because hydrogen only has one orbital.
Oh, okay. How big is that orbital in hydrogen?
It's not.
It's not big, right? So if I tell you that tin is below carbon, far below carbon on the periodic table, right? You can imagine that the orbitals that tin uses to bond are really big, right? It's in the fifth row. Bromine is also down there really low, so its orbitals are also really big. And so the orbital overlap between a bromine and a tin, because they're more or less in similar shells anyway, right? That's going to be much better orbital overlap. Hydrogen, remember, is really, really, really tiny. So you have this really small orbital in hydrogen overlapping with this really, really big orbital in tin. And so that's going to produce a relatively weak bond. Right? Tin and bromine being in the similar shells, orbital size is going to be a much better match, and then the bond is going to be way stronger. All right, so let's look at the mechanism really quickly. So AIBN is a bispecific This is going to degrade into two radicals in molecular nitrogen. So each of these carbon-nitrogen bonds is going to break, giving one electron to the nitrogen-nitrogen bond to make the molecular nitrogen, and then the other electron goes to carbon to make two of these nitrile stabilized carbon radicals. Right? Tributyltin hydride is going to react with this carbon radical, right? We have a weak hydrogen tin bond. And so the carbon radical that's produced by AIBN in the initiation step, it's going to pick up a hydrogen and now produce a tin radical. Right, and then this is a critical step where we're making the tin bromine bond. So that tin radical is going to reach out for one of the organic halides, right? Grab the bromine atom, leave behind a radical in carbon. Right? And then once we have that radical on carbon, we can replace that bromine that we just lost with a hydrogen by reacting with a molecule of tributyltin hydride and completing our propagation cycle. Right, so we reform our tributyltin radical, that's going to go on and do another dehalogenation step. And the chain continues. Questions about this?
Can radicals undergo rearrangement?
They can undergo rearrangement.
So if you were to add two methyl groups at the end of that butane, is that
We might get some rearrangement product, yeah. Other questions? All right, is that clock right?
It's
It's
8:50 on the dot.
It's 8:50, okay, so we're done then. All right, so we'll come back. We're going to try to finish up this radical chapter on Friday. We might leave a little bit until Monday.